Okay, hello everyone. It's 5 o'clock in Berlin, and welcome to our online hands-on workshop devoted to working with the RDKit and Knime analytics platform. My name is Daria. I'm a data scientist in the life science team at Knime. With me on the call is Greg.
Hello.
Who is also a member of our life science team, although only part-time. We're very sad about that. And he's devoting most of his time to the development of the RDKit chemoinformatics library. There are a few other Knimers with us on the call, and in case we run into some kind of issues, technical issues, hopefully this will not happen. We will do our best to solve them promptly. It is the first time that we are actually running this the workshop, hands-on workshop in an online format, so please bear with us in case there are some technical bumps. We'll find the solution. Okay, there are a few technical bits that I would like to walk you through that would help us to get the most of this session. And also it will give us another 2-3 minutes to let everyone else who is joining a bit late to join. So let me jump to the next slide. So before we start, we would like to ask you to use the Q&A section that is in the bottom of the Zoom window that you are using for the call to post your questions, and then you will see them, and also other attendees can see them in the Q&A section, question and answer section. And please upvote the questions, like your favorite ones that you think are the most relevant and interesting, or maybe if you're also encountering the same problem. And we will be answering your questions. So we will either answer them through this question and answer tool, or we will answer them live. So this session is recorded and it will be available on YouTube, and we will share the links with you after the webinar. Okay, so please download the materials for this workshop, and the link is available here. So it's also available in the chat so that every attendee can see it. This link redirects you to the Knime hub. So this is a central repository where which allows a big Knime community to share the workflow. So we use that one as well to deposit the workflows we will be working on, and also the workflows that we will demo today. So after you've been redirected to this page, you will see the repository. There is a folder, this 2020_04_21, RDKit Online Summit. So please click on this cloud icon and download the whole workflow group. So after you've downloaded that one, you're ready to set up the Knime analytics platform. So locate that file, that .knr archive, probably it will be in your downloads, and double click on it to open. This will prompt opening your Knime analytics platform and import those workflows, so that file, into your local workspace. So this would be the windows that you would be seeing there. And so just go ahead, continue, and import those workflows. And after that, go into your local repository and open the workflow that is in the folder Solutions, that is called 02 Multi-Parameter Optimization. In case you haven't used yet any chemistry or chemoinformatics type extensions, it will most likely prompt you to install additional libraries. So that would be then type of error message that you would see. So just go ahead and proceed with the installation. After the installation is finished, it will ask you to restart the analytics platform to make the effects. And just go ahead, restart, and you're ready to go. We also sent the links for the download of those materials earlier. So those links were not pointing to the Knime hub, they were pointing to the Dropbox folder. There is, if you already have them set up, great, nothing to do for you. We changed the link because we introduced like a really tiny difference in the main workflow visualization, so it doesn't affect anything at all. So if you have the workflow already set up, download it, import it into your Knime analytics platform, great. Just stick to it. If you don't have it yet, then use the links that you can see in the chat. Okay, the instructions are also in the chat. So then you can always come back and go through them while I do the introduction. Okay, so now let's go through our program for today. So first of all, I will give you a brief introduction to Knime, and afterwards I will go to the first part and introduce you the use case that we will be working on. So there will be an exercise in the demo devoted to the R group decomposition, and afterwards we will look at the possible solution. And as the second part, Greg will introduce the workflow to perform multi-parameter optimization for picking the compounds. And we'll do a demo of that workflow. So, brief intro to Knime. Knime Analytics Platform is the software for data analytics that is based on the graphical programming paradigm. So instead, what it means, instead of writing and compiling your code, you're actually building a workflow and you're using nodes to perform individual tasks in this workflow. There are many, like over 2,000 native and embedded nodes to perform those individual tasks. So there are tasks for data access, and where you can access and read your files located either locally or on the databases or in the cloud. There are also different nodes to perform transformation of your data row-wise or column-wise, to perform different manipulations like aggregation type manipulations, to work with different types of data like text, not only text data, but also numerical data, but also images, networks, and so on. There are also lots of nodes to actually perform analysis of the data. So different machine learning methods are implemented. A lot of nodes to visualize the data so that you can get insights. So there are, we will go a bit more into detail into those ones as well while we are doing the exercise. And there are also nodes to do deployment, sort of to actually make the results of your data analysis available. The Knime software infrastructure. So everything that we will be doing today is built in the open source Knime Analytics platform using Knime integrations, Knime extensions, and some community extensions. So they're all open source and you can do it locally. Once you would like to go and work more on the collaboration or then the Knime server comes into play. So it allows you to actually perform automation of the management and deployment of the workflow on a big scale. There are lots of additional resources that are available for you to get you started, sort of through Knime pages, Knime Hub, Knime Tech pages, and of course Knime TV on YouTube. I would also like to share a copy, free copy of an ebook, which is called Knime Beginner's Luck. And you can use the code KnimeWorkshops0420 to actually download the book. And the link is knime.com/KnimePress. The book code also you can see in the chat. Okay, we are ready to actually do some chemistry, and here is just a teaser of the first problem we'll be looking into today. It's the R group decomposition, during this exercise we would like to explore a data set, perform R group decomposition for it, and build this interactive view. So that's the first one, and the second one, what the Greg will introduce to us, is the multi-objective optimization using Pareto ranking to actually pick the best compounds. And there will be the other visualization using the wonderful parallel coordinates plot, which Greg probably will go into detail a lot. Okay, the first problem, the first part, R group decomposition. So the problem we are working on, you would like to perform R group decomposition for a set of compounds. So I assume that most of you should be familiar with the topic, and if not, if you have questions, please raise it in the Q&A. And so when you're doing the R group decomposition, you would like that this process is interactive. So you would like to be able to pick the R groups on your compounds interactively. You would also like to then visualize the results, and that those results can talk to each other and also summarize the information. And that this process is reproducible, sort of if you put then another data set into it, you don't need to redo your whole workflow again. So what would be our data and tools to do that today? The data you will be working with are the bioactivities for a single Campbell assay for the CDK2, so the cyclin-dependent kinase 2. The assay ID is also in the data, so it has the bioactivities, the PIC50 values there. The nodes that we will be using today. So the first of those ones will be the table reader, so that one reads tables in the native Knime format, and it really gives the maximum performance. So it's, I think, one of the fastest. It's the fastest reader, and it also actually gives you the minimum configuration. It is also important that all of the formats. So if you have your data saved in a special format and you would like to transfer it within Knime, if you do it via the Knime table, then those formats are preserved, so you don't need to do any more conversion from one format to another again. Important to, so the only thing that you would need to provide when using the table reader is actually the file path. And the file paths that we will be using in today and in the workflows, you will see they are all workflow relative file paths. What does it mean? So instead of using this local path, which would be very long, sort of pointing to my user folder, then workspace folder, another workspace, and so on, we just try to find the file where find in the file relative to the workflow we are working on. So as an example here, I have the workflow that is open, that is R group decomposition one, and the file I'm reading in is enclosed in this folder data. So I'm going, since every workflow is the folder, so when I'm writing the path, I'm sort of going one folder, I'm going outside the folder of the workflow. So I'm already in the folder of this exercises. And then I'm going into the folder data. And after that, I'm going to the file input.table, which is located in this folder data. And that allows to then access this file. There are a lot of advantages of using those workflow relatives paths, because it's actually like the best choice to share the workflows, because the only thing that you need to match is the folder structure. So for example, once I've shared with you the whole folder with the exercises and the solutions for today, and the files are referred to those used in those workflows, referred to their workflow relatives path. It doesn't matter like sort of how do you know where do you put this folder. They will all be accessible, so there will be no problems or errors that you can't find the file. Okay, the next node that you will be using today is the RDKit MCS node. So that one allows to extract the maximum common substructure from the structures in your data table. So you have to specify a column with your structures and then perform search for the MCS. The code allows strict and fuzzy searchers, and this is you have to define that by using the configuration dialog of the RDKit MCS node. So in these options, you can see, for example, the threshold option, or like ring matches ring only, or complete rings only, and so on. And like, for example, the threshold option means that which fraction of the molecules in this column should match that MCS. So for example, if you have 1 there, that means that all the molecules, so the MCS should be present in each molecule. I have, for example, on the slide here 0.9, which means that the MCS should be present in 90% of the molecules. And so on and so forth. So for example, there are also ring matches rings only, so that's for the ring bonds and like how the rings should be matched, how the atoms should be compared, how the bonds should be compared. Okay, so after you've performed the RDKit MCS, so the search for the maximum common substructure, you can view the output of that by like right-clicking on the node and then go into the very last menu of that, and that it will say MCS of the input structures, and you will have a data table with 1 row with the picture of your maximum common substructure that is found, and some annotations to that, so number of atoms and bonds in it. Okay. So this MCS would be very useful for the R group decomposition, because that will help you to define sort of the core of your molecule, and then you can use the R group decomposition to actually then define what would be the R groups around this core. So the node will again you will need to configure it, so you will need to specify which column contains the RDKit molecules to search to find the R groups in it, and then you will also need to specify the smarts or of the core. So you can do it by like pasting it in the window here, or you can, for example, import an additional table which has smart smiles or SDF of the core, and it could be 1 or multiple cores. So after you perform the R group decomposition, what happens, you get an output table where you have, this was the column of your core. And then there are the new columns are added, and they represent your R groups. So here are 1, R2, R3, and so on. So in this case, 7 R groups. And of course, you can do that manually, so that I go back and specify this the smarts of the core manually, but it would be also very nice to control that dynamically. And you can control it dynamically by using flow variables. And you do that by using the flow variable tab in the node. So that will allow you to control the value of that smart pattern by a flow variable. How do you obtain the smart pattern as a flow variable from your RDKit MCS node? You use the table row to variable node. So this node will take as an input the table, actually only the first row of the table, and will transform the content of that first row into flow variables. What does it mean? That the column names will become the flow variable names, and the column values will become the values of those flow variables. As shown as an example, as shown in the example here, I have the output of the RDKit MCS node with the maximum common substructure, and then I apply, so I execute table row to variable, and I look at output variables there. So I have my first variable MCS, name MCS, so corresponds to the column name MCS with the value of it, and this is the smarts pattern of the scaffold here. And so then also there are some more flow variables. And so by this, I have my flow variable that carries the smarts pattern of the core, and then I can use this flow variable. I go back to one slide to configure my R group decomposition node. So what it helps me to do, so when I have a new data set and like a new core comes in after the MCS, I don't need to change it manually. Okay, let's look again at the data that we will obtain after the R group decomposition. So we have the table with the cores and the R groups presented. And so like each column represents a certain R group. And there is the spec of those columns. So we have in total like 15. What would be interesting actually to see is a pivoted representation. So for example, we'd like to aggregate the compounds with a pair of selected R groups. So we look, okay, which compounds have a substituent like R1, and then, for example, I think in this case it's R5, and how many compounds have this following R1 and this following R5, or this R1 and that R5, and sort of to get an idea how many compounds there are in the data set with those. Or, for example, we could aggregate what are the IC50 values of those compounds, what are their means, or what are actually the compound structures, and so on. So how one would do that? In Knime, one would do that using the pivoting node that will perform the pivoting on selected columns. And you have to define what would be your groups, so what would be your unique rows and what would be your unique columns. So in our case, that would be then our two R groups, sort of those that we would choose on our scaffold. So for example, if we're looking at the scaffold and then we see like, okay, we want to substitute on one side and on the other side. And then we aggregate the information. So with respect to what should be set up, the node has then several tabs in the configuration dialog. So there is a group tab to define your unique rows. There is also pivots tab to define your unique columns. So in that one, I would put then my first R group and the second R group I'm interested in. And after I've defined that, I go to the third tab that actually allows me to aggregate the data. And in this case, I will be only aggregating the counts of the PIC50s. So basically how many compounds are present with those two substituents. There is also an option to enable highlighting in several nodes that allow aggregation. What that means is that after the aggregation, the row IDs they will be mixed up or they will be actually lost. If you want to keep them in memory, and that would be useful to perform visualizations later, you enable this option, enable highlighting, so then the original row IDs from your data set are recorded. And it would mean that, for example, in your output table, once you do the visualization and you want to look at those 6, for example, compounds that have the substitute like in row 2 and in the first column, you still can go back and see what are those compounds with those R groups. Okay, let's remind ourselves. So now we've performed pivoting first, so where we have a table with the pair of R groups. And then we also we have a table from the R group decomposition, where we have our original data, then plus each of the molecules have additional columns that represents the core and represents the R groups. What we would like to do is to build the visualization for interactive visualization for that. We would like to see this pivoted table. Then once we click on the row in this pivoted table, we would like to see a picture or pictures of the molecules that have those R groups in those particular position. It would be also nice to see the MCS of that main scaffold. And then at the end also is a table of all the compounds with all the other R groups that are present specified. Okay, for building the visualization, we obviously will use the data visualization nodes. And as I promised you some time ago, to go a bit more into detail, there is a very large selection of the visualization nodes. They're web-based and interactive, so they're JavaScript. There are also integrations of the Plotly nodes. There are also nodes that allow to do your visualization using your R or Python code. So if you want to really do some customizable graphics. One of the nodes that we will be using today in the visualization is the table view. So that will allow you to display the data in the HTML table view. And that view will offer several interactive features, as well as the possibility to select rows. So once you executed the node, the interactive table view can look like that. Each JavaScript visualization node, so its configuration dialog looks similar. So usually you have the first tab that shows you general options of the that are specific to a visualization type. So for example, that is the table view. So I can, there in like red and green, I can pick which column should be included or excluded. Yeah, I can also like give the title to the table. I can say like if I want to display the colors of the row or the indices of the row, if I want to display the row keys, how I want to the column, the data in general to be displayed. But there are also some additional tabs, and one I have to actually keep that in mind when also doing the exercise and configuring the view. So for example, those that allow the interactivity of the view, sort of that you can allow pagination of your results, or like the selection, if you allow multiple selection or a single selection. So how many entries could be selected. And also there is a formatters tab that actually formats globally your data. So for example, it's very useful to define how your numeric data, so the double numbers and double formats would be represented. So how many decimal places would be shown, otherwise your data can get really, really long. Okay, selection and filtering in JavaScript view. So the selection is by default propagated to all other views. So for example, you select the row, and then also this selection will be also shown in all other views. So for example, if you selected something in the table, and then you will see the same selection in your tile view, on your scatter plot, or other visualizations that you have. And you can, when you would like to close the view, if you want to keep the selection, you click apply, and as the output, you will get in the output table this notation, so it's true or false, so it's selected or not, and then you can use that information for your downstream nodes. Okay, the other node that we will be using for visualization heavily today is the tile view, and the configuration dialog. I'm here only showing the first tab of the configuration dialog that displays the options, because the other two, like interactivity and formatters, are basically very similar to the other ones that you've seen already in the table view. And this one will allow you to actually display your information as a tile, which is very useful if you want to display the images of your molecules. So for example, we could configure it the way that we would only show one tile per row, and this is what is happening here. So instead of, so we only seeing one molecule, we're only displaying also one entry. We display the column headers, and we also display here the information. So I would like to see my PIC50 values, and for example, as a title column, I would like to use the column carrying the compound Campbell IDs. So that's displayed here. And so we encourage you to actually play around with the settings and try different ones when you configure that. Okay, how do we build combined views? For that, we use components. And you can combine multiple the JavaScript views, so just by selecting and wrapping them in a component. And then when you open that interactive view, the selection will be transmitted to all other views. So for example, here I picked a compound in the tile view, and now immediately I can see how many data rows in the data table are selected. Also, those components are very powerful in the web portal, because each interactive view of the component becomes a web page in your web portal workflow application once you deploy this workflow to Knime server. How do you configure the layout and the content? So what is displayed in the interactive view? You need to go inside the component. So open the content of component, and then you click on the layout editor button on the toolbar, and this will open the node usage and layout editor. And there you can add views and rows like via drag and drop, and like how it should be configured literally, so from left to right, back and forth. So you will have also a chance to try it just now. Okay, so now you are actually all set to try to start doing the exercise. So how we will proceed from now on. So we will open the workflow, and workflow contains the instructions to follow and to perform the exercise. So if you have problems, ask questions in the Q&A and upvote those questions. We will first give you now 5 minutes, and we will not be answering any questions while you are starting the exercise. So until like 20 to 6. And then afterwards we will start going through questions one by one with respect, like which of them are sort of refer to the beginning of the workflow to the end. And then in 20 minutes, I will do a demo. So at 5 to 6, I will show a possible solution of the workflow. So let's go and open the exercise that is in the folder. So in your local workspace folder of the folder with the workflows, go to the folder exercise and then 01 R group decomposition. So let me open that one. I go to my Knime Analytics platform now. So, and here in my local workspace, there is the folder that I imported. So with the exercises and solutions as well. And the exercise that I would like you to start with is 01 underscore R group decomposition. So here is the workflow. I'm gonna close that one as well. And it contains the instructions. So I can make it a little bit larger so we can see. And we can see, okay, there is several parts, several bits. So for example, there is a first bit to compute the MCS. Then there is a second one to perform R group decomposition. Then there is a third one to find how many molecules with each combination of the two selected R groups are in the data set. So basically to perform pivoting. And then there is the very last bit to actually create the composite view, so to create an interactive view. So go ahead and start with the bits and we will be there to answer your questions. I'll remind you, we'll have a look at the possible solution. It's just like 5 to 6, or maybe actually 6. Let's see how we go. Okay, so I just opened the workflow that is located in the folder solution in the, and that is called again then 01 R group decomposition. So this one doesn't have all the instructions. It just has those 4 groups sort of to compute MCS, perform a group decomposition, pivot, and visualize. So we are starting by reading in the data table. So I'm going to execute the node. So if I go in the configuration dialog, so that is exactly the Knime workflow relative path pointing to this input data table. That is then located here in the folder data. And I assume for you it would be actually the same. So how does the data look like? We have here the table with 91 rows so for the molecules. We have the column with canonical smiles, compound IDs, molecular reg number, so that's a Campbell identifier of the molecules, the relation to the PAC50 value, the PAC50 values, and the information about the assay. You can also see that information in the tab spec of the output. Okay, so how we would compute the MCS. So I would next configure the RDKit MCS node. So I'm using the fuzzy search. So I'm looking through the, I would like the MCS to match 80% of the molecules, and that the ring atoms will only match the ring atoms, and that only complete rings are matched. And with respect to the atoms, I will compare any atoms. So for example, on the aromatic rings, the aromatic carbon would be compared to the aromatic nitrogen. Okay, so after I execute the node, and I have a look at the output of the node. So I can do it in two ways. So one that I showed on the slides by right-clicking on the node and then go into the last menu, so MCS of the input structures. And then here I have my data table with one row. I have here the smarts, so the visual representation of the smarts. This is done because of the rendering. So if I right click on that column and I go, for example, available renderers, so by default it is rendered by Marvin. Since I have the extensions installed, it could be also, for example, rendered as a string, or if you have any other visual chemical tools, so for example, that could do visualizations, the RDKit, and the format is in the RDKit molecule, and it could use the RDKit visualization. So there are a few buggy symbols there, like ampersand and @ that correspond actually to the aromaticity of those bonds. Okay, so next what are we doing is we only transferring that table to flow variables. And now we are ready to do the R group decomposition. For that, we need to configure the RDKit R group decomposition node. So the molecule, the column with the input molecules is called canonical smiles. So that's how it comes from the input. And then the core smart, we're gonna control it actually by the flow variable. So in the flow variable tab, I'm looking for the smarts value of the smarts value variable, and there I'm using the MCS flow variable. So that's the flow variable that as a value carries the smarts pattern. I can also check it here on the output of the table row to variable node, that the flow variable, which name is MCS, the value of it is actually my smarts pattern of the core scaffold. And so I will execute the R group decomposition node, and I will explore the molecules that match the R groups. So there is 91 molecule, so all the molecules matched. And here I have the core, the same image as before, and then I have my R groups. So we can see that some of them have hydrogens or so on. I mean, we could make that a little bit larger, all of them. So if we would like to see a bit more, like by pressing shift and dragging it. Okay, and so now we're done with the R group decomposition. There is also a point of this RDKit for molecule. So I would like to actually convert the smarts into the RDKit molecule. That would improve the visualization. So I am converting the smarts of the core, and this would then show up this way. So let me move the column here, and just looks much nicer. And we can exactly see, for example, that here is on the where the R groups are actually positioned on the scaffold, and that could be very useful. So exactly we have first, second, third position on our fused ring. Then we have also fourth, fifth, and sixth on the benzyl, and then we have the seventh. I think it's probably the amino group on the amino group there. So let's pick the R groups for visualization. So for that, I'm going to execute the pick R groups for visualization component and open its interactive view. So I executed that by pressing this play button on the toolbar. And then here is again the picture of the main scaffold. And I would like now pick the two groups. So I will pick the first one and the fifth one. So the fifth one is in the para position. So hopefully there are no symmetry issues. Okay, so now I'm going to close the view and I will apply the settings. So I will keep those changes for the next node so that they're projected. So if I would now explore the output, I have here again my table. And now my two columns that I will be used for the grouping are converted here to the smiles. Okay, so now let's do the pivoting. So let's aggregate the counts of the compounds that have those two pairs of substituents. And so for doing that, so I could manually, for example, select those two columns. So R1 and R5. Or I could do it using flow variables. And for that, I need to actually find the proper flow variable. So I know that one should be in the group columns, and then that's a variable included list, so that one is R group 1. And then the other one should be in the pivoted columns. So I go through the flow variables list and I look for the pivot columns. So there is my R group 2. So now the values that will define my rows and columns are controlled by variables. There is a third setting that still should be adjusted. That's the manual aggregation one. And I'm aggregating the counts of the PIC50. Basically, I have a column here of the PIC50, and I just added it to the aggregation tab, and then I selected the counts there. Okay, I will remove that one so we don't change the settings. And there was another thing, most important, enable highlighting. Otherwise, the things would not be protected. The raw IDs would be lost. So I execute the node and I explore my pivoted table. So my R1s are now the row IDs, and R2s, or like R5 actually, are my column headers. So and the table is filled up with the counts of the PIC50s. Okay, so now I would like to build the visualization from those tables. So we have our pivoted table, and then we have also all of our data. So that's the second table where we have the course with the individual groups and also all other information about the input molecules. So there are two pre-processing steps. So for example, the first one, and also there was a very interesting question before that Craig answered, where we actually embedded the images of the R groups into the table. So I'm just going to execute that one and not go into detail. Although if you have questions, ask. And then in the second meta node, we are rendering all the R groups to images. So that's basically just 5 or whatever respective 7 renderers. Okay, so now the visualization and the component, let's go inside what we have. So we have a table view with the pivoted table. We have a tile view that will show us a core scaffold. We have a tile view with the selected molecule from the pivot table. And we have also all of the selected molecules that are picked in the pivot table. And the layout, we configured it using this node and usage icon. So that opened us the the window to actually change that, so that I would see my pivot table on the top, the molecule and the scaffold just in the middle, and then the selected molecules in the bottom. And like as I was promising you, one could, for example, add additional views and change those layouts and drag the, for example, elements in and out and so on. Okay, so now let's have a look how the view actually, what it would show us. So I'm executing the component and opening the view. So at the top, I see the wonderful table where I have here the R1s. And then in the column headers, I have the R5s. So let me just pick one of them. So for example, if I pick just the first one, which has only one compound, then I would see that pick the image of this compound with its IC50 value in the tile view, the MCS on the right side, and then I will see here the table with the compound Campbell ID, and it substitutes like all the individual R groups. I mean, we could also add, for example, more information to this table. One could add all the information about assays or whatever computed molecular properties that you have. So for example, if we pick now the second row, then there are two molecules with those ones, and they are also shown here on the tile view. And so we can see also the difference between them. So the first one having the position of etoxy, and the other one using the metoxy. And we can see that those ones are exactly in the position R1 and R5. Because this is our R1, this is our R5, so that it's H, but there are two compounds, and one of them, the second of them actually has the metoxy in the fourth position. And if we look here, there they are. So first substituent is this toxy, and then there is difference in these two compounds. So one of them has, okay, it's not fourth, it's sixth position, the metoxy substitution here. Okay, so that was it.
Daria, can I make a quick comment before you close the view?
Yeah.
The same question has come up a couple of times about what the enable highlighting does in the pivot table. And the best way to understand that is by looking at what happens in this view.
Yeah.
So this is a little bit technical for people who aren't concerned about the technical stuff. You feel free to drop out a little bit. But what happens when you click on one of the rows in Daria's pivot in the table in the view is it sends a message saying which rows you just selected, and it sends that message to all of the other views that are open at the same time in this component. And they can then do that. They can use that message to control what you see. So both of the views, the tile view and the table view that Daria is using, are selected to show only rows. They're set up to show only rows that have been selected. Mm-hmm. That selection information is done using row IDs, and it's done using the row IDs on the tables. The problem is when you do a pivot, you take a bunch of input rows and you reduce it into a different number of output rows. And those output rows have different table ID, different row IDs. What you do if you select enable highlighting is it saves the information about what the original row IDs were, so that when you click on something, when Daria clicks on something in the R group table and the pivot table, it knows to send messages about all 9, in the case of the row she selected, all 9 of the original row IDs. And that way the other views can react to that.
Yeah. I mean, we could also demonstrate it actually by unclicking the pivoting or unclicking the enable highlighting. Then to see, because they come from two different tables. So if they would come like the data comes from one table, then it would still know the row IDs. But since our pivot table comes as the output of this node and the rest of the data as the output of that one, so if we didn't enable the highlighting, that we would have lost all those information after the aggregation. Do you think I should actually enable? So here, if I click on disable the highlighting part, and I will look at my component again. So let me execute it. I need to execute everything. Now I will open the view, right click, interactive view. And now if I try selecting something in the pivot table, nothing comes out in the tile view. This happens exactly because the row IDs are not kept after the pivoting, and so the the table view doesn't know anymore to which row IDs those aggregation counts refer to.
Okay, what I'm going to do is do a brief overview of a way to use Knime and some of the community contributions, the RDKit, together with a set of community contributions from Eli Lilly to do multi-objective optimization, or specifically to do multi-objective ranking in Knime. Let me give you a little bit of an introduction to the problem first, and then I'll share the workflow. So what we're trying to do is we have a set of compounds, and I'm going to provide a set of compounds in the workflow, and we want to pick a few that we're going to be doing more work on. So these are some compounds that we think are interesting, but there's too many of them and we can't follow up on all, so we need some way to rank them in order to select which ones to do more work on. In the project this hypothetical project that we're working on, we have a couple of different models available for predicting things like ADME and toxin points, as well as physicochemical properties. And the goal is to use those models, as the ADME and tox models, as well as the physicochemical models, to predict a few compounds that'll be the best ones for us to follow up on. And there's a question about how to do that, because we have all of these different inputs. So if we had a single model, which was just the affinity for the target of the that we were working on, it'd be pretty easy, right? We could just take our compounds and rank them according to that model and pick the best ones. But we have multiple models, and so there's a question about how to do that. Specifically, what we're going to do in this exercise, the models are, the three models are one for HERG, one for a CYP, so for 1A2, and one for human clearance after IV administration. The properties that we're going to use are log-P, TPSA, rotatable bonds, and heavy atoms. More specifics for if you really care. The models, I'm not going to share as part of this workflow. We're not going to talk about in detail about the models. I'm happy to share the workflows that I use to build these if you want, but this is the details of what I did. For HERG and the CYP model, these are both built using XGBoost with an RDKit count-based Morgan fingerprint. And then for the clearance model, it's also XGBoost, but it's using the RDKit 2D descriptors. A disclaimer at the very beginning, these are not necessarily the most interesting endpoints that you'd want to use. And these are certainly not the best models that you can possibly build for these endpoints. The accuracy of these models is not great. I wouldn't really want to use these in production work. So though I'm sharing the models with you, I wouldn't recommend you use them in real life. They're really just being used here to demonstrate the method. So what is the method? We're going to do multi-objective optimization. And what that means is we want to pick a set of best points given that we have multiple objectives or multiple scores for those points. So I show here just a very hypothetical simple example in 2 dimensions. This is always explained in 2 dimensions because it's easy to draw. P1 is one of the things I care about. One of my objectives where better is things get better as you move down. P2 is the other thing that I care about, and here things get better as I move to the left. And I have all these points, and the question is, some of these are better along one dimension and some of them are better on the other. Which ones should I pick to follow up on? Which of these points should I pick? And it turns out there's a nice way, or there's a nice well-defined mathematical way to pick the best from this, or to define best. And that's using what's called Pareto optimization. I'm not going to get into massive detail here. There are 2 links down at the bottom to Wikipedia pages that are actually quite good explanations to this, and include, as usual in Wikipedia, plenty of further references if you want to read and read and read. I'm just going to show you for this simple example what we would end up picking. So what you do for each of the points, you score along each of the dimensions so that 0 is the best possible value. So that's exactly what I was doing already with P1 and P2. They both get better as you get closer to the origin. And then for each point, you draw a line from it to each of the other 2 axes, and then you just count the number of other points that are inside the box formed by those 2 lines. So for this point, you can see the box it forms, there's no other points. So this has nothing inside. This point, this point with no outline, has, when I draw the box, it has 1 other point inside. This one also has 1 other point inside. The one up here, the one that's white in the middle, has 2 other points inside. So what you do is for each point, you count the number of other points that are inside the box, and then you just rank them in decreasing order by that. So the compounds that have, increasing order. Compounds that have nothing between them and the origin, these are the points on the so-called Pareto front. Those are all rank 1. These 2 points that have 1 point between them and the origin, in the Pareto theory that says they are dominated by 1 point, those are rank 2 in this example, and then this guy that has 2 points between it and the origin is rank 3. So it's pretty simple. You just draw these boxes and you count the number of things that are in between, and those allow you to rank things. And this is the approach that we're going to be using in our workflow. It's pretty easy to do this in Knime. You could sit down and probably do this with a Python snippet or a Java snippet if you're really highly motivated, but fortunately you don't have to, because the folks at Lilly, as part of the Earlwood open source cheminformatics nodes, did a really nice node to do this for you. Here I'm showing the page from the Knime hub that explains what the node does. Just to motivate all of this. The configuration dialog for this, this is the way in which we are going to use it, and I'll say some more about it when I actually show you the workflow. But the configuration dialog allows you to pick for each of the columns in your table which ones you want to use, and for each of them say whether you want to minimize that value, maximize that value, or if there's an optimum range for it. And we'll go through this in a little bit more detail when I show you the workflow. This is a picture of the workflow. Pictures are boring. Let's actually go look at the thing live. So let me switch to Knime. That's Daria's workflow, and this one's mine. So here we have the workflow. This is the same one I shared with you. The table creator just has a set of molecules. This is just to provide some input. This is a set of molecules that I pulled from Chemble. So what I start by doing is I read in my molecules. Let me just go ahead and execute that. And then I need to generate the values of my parameters. So I have my 3 different models. I have the clearance model, the SIP model, and the Hurd model. I'm going to run each of those models on the compounds in my table. So I can just go through them. I'll do them do the first one individually so we can look at what comes out of this. So for the clearance model, it has, let me show you actually, sorry, I should start by showing you what the input data look like. This is my input table, which will eventually show me that it has Chemble row IDs and the smiles column. The reason it took so long to load is that this molecule, the one in the 4th row, is an absolute beast. I shouldn't have picked something this horrible to include in the demo because it really challenges all the software. Anyway, that's there. It is what it is. We run that through the clearance model, and what comes out the other side is the name. That's the name column that was read in. And then from this model, it's a classification model for clearance, and the target value is low. So is the compound likely to be low clearance? If this last column has the actual prediction, and then what we're actually going to use are the predicted probabilities. So this column is the predicted probability that the compound is not low, and the second one is the predicted probability that the compound is low, so low clearance. And we're going to use these predicted probabilities as the metrics in our multi-parameter optimization. So that's the clearance model. The CIP model is the same thing. It's just going to predict whether or not the predicted probability that a compound is a CIP inhibitor. I join those two together, so now I have a column of more rows. I run the herd model, so more columns. I run the herd model. I now have a table with even more columns, so we can take a look at that. We have now did I make a mistake? Oh no. In the joiner, what we have is the predicted probabilities that we're going to be using. I didn't bring all the columns over. So there's the name, predicted probability that its clearance is low, the predicted probability that it is a CIP inhibitor, and the predicted probability that it does have a low hERG IC50. So it does inhibit or at least interact with hERG. I also calculate a bunch of properties using the RDKit descriptor calculator. Using the RDKit descriptor calculator. So log P, PSA, number of rotatable bonds, and the number of heavy atoms. And I join those on with this joiner. And now I have my final table. That has the columns that I care about. So for each of those molecules. Now I want to do my Pareto ranking. So the configuration here, when I start this, let me add a new one so you can see what it looks like when I start. So this is a Knime pro tip in case you don't know how to do what I just did. I frequently like to work with Knime where I see just the workflow and none of the other stuff around it. That means I don't see the node repository. So if I want to add a new node, I can either go and open the node repository by clicking over here, but I find that kind of fidgety. So instead, what I do is I select the node, or I select a node that I want to connect something to. I hit Control space to search the node repository. On the Mac, that is Command space. And then I can start typing what I'm looking for. So in this case, if I say I want to add a row filter after this, I select row filter, and if I double click, it will add it to my workflow and add it connected already to the last node I had selected. So there's added value to this workshop, a bit of Knime usage pro tips. So anyway, when I start the Pareto ranking, what you see is there's no column selected, so I have to add all the columns. I'm not going to do that manually here. I'll show you what I chose in the actual workflow. So I'm going to optimize. I'll start down at the bottom with each of the models. They're simple. So I do not want my compound to be low clearance. So I want to minimize the probability that it's low clearance. I do not want it to be active against CYP1A2, so I want to minimize the probability that it's active against 1A2, and I definitely do not want it to be a hERG binder, so I want to minimize the activity against hERG, the predicted probability that it's a hERG binder. If for whatever reason I was trying to kill people, I could change minimize to maximize and try and optimize for things that bind to hERG. For the other ones, number of heavy atoms, I'm also trying to minimize, so I want molecules that are small. Number of rotatable bonds, this one people often also sometimes minimize. I like to try and get at least one rotatable bond in a molecule, so it's not just a big flat aromatic plane. So I have a minimum number of 1, and then let's say a maximum of 4 for that objective. Log P between 0 and 4, so I want it to be polar but not super greasy, super polar. And then PSA, these are two magic values for PSA. One of them has to do with not penetrating the blood-brain barrier, and the other one has to do with just general likelihood to be biologically active. These are all rules of thumb that one should take with a very extreme grain of salt. But we're using it as part of the multi-objective optimization, so none of these are going to dominate any of the other ones. I can run that, and if we look at the output, now this has just added a single extra column to the table, which is the Pareto rank. And that's that rank that I described in the slide, the PowerPoint slides. In this particular case, because I have a lot of dimensions and a small number of molecules, I don't end up with very high Pareto ranks. Basically, everything is low ranked, which is good. So I could have gotten some higher Pareto ranks if I'd chosen less objectives here, but I just want to show generally what this looks like. But you should be aware that if you have a very high dimensional space like I have here, so this is a 7-dimensional space, it is very easy to have all of the molecules be rank 1 in a high dimensional space like that if it's super high. Now I want to get the structures. I always want pictures of molecules. So I'm going to join the molecule information back on with this joiner. And then we want to view and pick some molecules. So that's I'll just show you the view and then we can look inside later. This is going to show my favorite one of Knime's visualizations, which is the parallel coordinates plot. Daria always laughs at me because she knows I try to get this into every presentation that I do. But if you have a low number of dimensions, say more than 2 but less than 10, this is a really fantastic way of looking at your data. So if you're not used to this plot, each of the lines in here corresponds to a particular compound. So I can select one of these lines. If I'm very careful, sorry, I'm using a touchpad instead of a mouse, and it's a bit hard to do. But if I select it, you can see the compound. And you can see for that particular compound, it was Pareto rank 2. Here's where it showed up on the CIP probability, the clearance probability. Here's for the other 2 models. It's not too bad on log P. It's pretty low on PSA. It doesn't have any rotatable bonds, and it's a moderate number of heavy atoms. So it's just a nice way to see the relationships. And if I click back in here on nothing, it'll hopefully deselect that. Again, I'm back to all of the rows being visible at once. I've colored the rows based on the Pareto rank just to make it a little bit easier to see. In this particular case, I'm not going to pick anything that's not Pareto rank 1 because a lot of the compounds are there. So I can just click on one of the axes and drag out a region, and it'll select everything in that region. So you can see here are the compounds that are Pareto rank 1. And now I can go in and further down select the set of compounds I'm looking at by selecting on another axis. And this is one of the things I think the parallel coordinate plot is the best for, is it makes it very easy for me to go in and say, okay, I've already selected all the ones with the low Pareto rank. Let's say I also really care that the predicted herd probability is low. So I now just removed another compound. So I'm down to an even smaller number. And I really do want something to have at least 1 rotatable bond. So let's pick those. And so you can see what I'm doing here is I've done my selections that I'm filtering along all of the axes, or I'm filtering along 3 axes at once, which is just kind of a cool thing to be able to do. And the parallel coordinates plot makes it easy to do that. Okay, Daria, I'm done saying nice things about parallel coordinates now. I'm going to now move on. These are the 4 compounds I'm going to move forward with. So let me apply this, or I'll just close this and keep it as a new default. So when I restart, I can see that. Now what I'd like to do is remember why I picked those compounds. And this is, I'm going to show another node that I think another view that I think a lot of people don't know about, which is the table editor. So in Knime, we have this HTML table view that allows you to see a table in one of these components. but also in the web portal. But you can also have, there's a table editor that's kind of the same way, except for you can mark particular columns as being editable. So I can go in here and take notes about these molecules. So let's see, we'll pick this one because I like OH. And this one has a chiral center. And I'm not doing anything serious here, obviously. But so now I've changed the contents of the table. And when I save this, that'll be saved to the output table. So now I can take the compounds that I picked and the notes that I took about them, I have in my output. You can see here that I have the notes in the output table. And now I'd like to save this for later use or to send to someone else. Unfortunately, that often ends up being sending stuff to Excel. So I'm going to use the Excel writer. So I'll write this out to Excel. And I've configured the Excel writer so that it automatically opens up the Excel for me after it saves the file. So you can see I now have all of the compounds along with all the extra data that was generated about them are now in Excel. And I have pictures of them there, so I can now send this to my colleagues or save it for further work. That's basically the workflow. You guys have a copy of it. When Daria and I were talking about this, we weren't sure how much time there was going to be left, so we didn't think it made sense to have you try and customize this or work on it yourselves. So we thought it'd be better just to show you the final workflow. You have it available so you can work with it and play with it on your own, but we are more than happy to answer questions about it.